In this video, we're going to look at vectors in a plane. In particular, we are only looking at 2 space at this point. Our next video will be in 3 space. This video, we're going to be in 2 space. So vectors have 2 parts to it. It has both a magnitude, that's the length of the vector, and then it also has a direction. The way that we're going to describe the magnitude notationally is it may have double bars on either side of our vector u with a arrow over it, or it may have single bars with a bold V. Or U, it could have been a bold U, it doesn't matter. That the arrow above it means it's a vector, or if it's bolded, it means a vector. So what a vector represents geometrically is a line segment that has a length and a direction. So if we take a look at a vector that is described by this first point and the second point, and this tells us which direction we want to go in. We start at point P and end at point Q. To get from the beginning of our vector to the end of the vector, I need to go a distance of positive 3 in the x, and I need to go a distance of positive 4 in the y. So this is how we could describe the vector if we put this point and force it down to the origin. It would be 3, 4 with these more almost inequality type brackets. We can describe this vector with this other set of ordered pairs. It is -2, 3, and 1, 7. I still go over 3 positive in the x, and I still go positive up 4 in the y. These are the same vector because it has the same magnitude and the same direction. When we put our vector down to the origin, we say it's in standard position. And the location of the end of the vector, the tip of the vector, is the ordered pair v1, u1, or u1, u2, or v's, or whatever you want to call your vector. So we put them in brackets, and when we see it in brackets like this, these almost like inequality brackets, then we make the assumption it is a vector in standard position, which means the end of it starts at the origin and it ends wherever that ordered pair is. So that's what we call standard position. And when we talk about the components, well, the components of the vector is the x piece and the y piece. The first one and then the second one, when we go in 3 space, it'll be x, y, and z. So if we want to go from the initial points to the component points, we take the terminal side or the ending value, where the tip of it is, and subtract off the points that are the tail, the beginning points. And so we get the components like we did up above. What a unit vector is a vector that has a length of 1. So a length of 1 means that we can take any vector and scale it down. And the way that we scale it down is we divide by the magnitude of the vector. So we find the magnitude of the vector, we divide it into each component of the vector, and then we have a unit vector, which means it now has a length of 1, but the directionality is maintained. The process of using scalar multiplication to find a unit vector is called normalization. Standard unit vectors is another one that we need to talk about. Standard unit vectors means that we're now going to write it in ij form. So in R2, the I vector is 1, 0, and the j vector is 0, 1. With a linear combination, we can take any vector v with its components x, y, and turn it into the standard unit vectors. So there'd be the I part, the x part times I, and the y part times j. So if I'm asked to determine what it is in the component form and the standard unit vector form, what they're asking me to do is first find the x, y parts as if I were to put it down at the origin and then write it with the I, j form. So the directionality does matter. To find this in the component form, remember it is my tail, there's my tip minus my tail. My tip is where I end in Q, so this is going to be my x part of Q, which is 1, minus my initial part, which is my tail part, and then of course I have the 5 minus the 3. This then gives me 2, 2. In the ij form, it is 2i plus 2j. Let's take a look at the next one. R is where I end. P is where I start. So my R is -3 minus a -1, comma, and then it's going to be 7 minus the 3. So this gives me negative 2, comma, 4. If I did my math right. You got to watch me, I'm sketchy. Which gives me negative 2i plus 4j. We can write our components in terms of the angle that is formed. The way that we do that is, like we do before, is that we consider the cosine of the angle is x over r. When we're talking about vectors, that r is the magnitude of my vector, where the magnitude of my vector all day long is x squared plus y squared and the square root of it. So I can take any one of these vectors and write them into the trigonometric form, which would be, in the ij form, would be the magnitude times the cosine of my angle times I, the magnitude times my sine of my angle, and then the j part. So if I want to find the component forms of the vector with a magnitude of 6, so that when the vector is plotted in standard position, it lies in quadrant 3, and it makes an angle of pi over 6 with the negative x-axis. A couple of things that are going on here. So the first thing is they're giving us the reference angle. This is the reference angle in quadrant 3. That is this. This is pi over 6. That is not the angle I use. The angle I need to use is the 7 pi over 6, because that is the angle in quadrant number 3 that has a reference angle of pi over 6. So they have the x part, so they're asked to find it, the components. They want us to find the x part, which is going to be equal to the magnitude of my vector multiplied by the cosine of the angle that is formed. So in this case, it is going to be the magnitude of 6 times the cosine of the 7 pi over 6. 7 pi over 6 is on the unit circle, so I can just pull that information off the unit circle. If it wasn't, then I would just put that in my calculator. And it is, so it is 6 times. I go find the 7 pi over 6. This is going to be negative square root of 3 over 2, which gives me, when I reduce it, negative 3 root 3. Now I'm going to find the y part. The y part is going to be my magnitude multiplied by the sine of my angle. So it's going to be 6 times the sine of 7 pi over 6. Again, the 7 pi over 6 is not on my unit circle, then I just put that in my calculator. But this case, it is. So this is going to be equal to 6. 7 pi over 6 is negative 1/2, and so this is going to be negative 3. The component form then is negative 3 root 3, comma, negative 3. If they asked for it in the standard unit vectors, which it did not, it is negative 3 root 3 multiplied by the I, and then, oh, sorry, that should be a negative. That should be a negative. Let me erase that and make that a negative. So then it is a negative 3 in the j direction. In this one, they want me to find the vector in this form. So it is going to be my magnitude out front and then the cosine and sine of my angle. There's going to be times in which we're definitely going to want to use this, especially for application problems. So the first thing I need to do is find my magnitude. So I find my magnitude, and it's going to be the square root of my 3 squared plus my negative 4 squared. And this is going to be the square root of 25, or in other words, 5. So that is my magnitude. I need to figure out what the angle that is being made. Now this is not going to be on the unit circle. So I'm in quadrant number 4, and I know that because I have a positive 3 and a negative 4. So this is where the vector ends. The angle I want is this angle, or I can use this angle. Typically, though, we usually use the positive, and in particular, they're asking me to find the positive. So what I'm going to do is I'm going to find the tangent of my angle is going to be equal to the negative 4 over 3. This goes back how we define tangent in terms of x, y, and r. So that tells me my theta is equal to the tangent inverse of negative 4/3. Now I've got to make sure that I have my calculator in radians, because or in degrees. This wants me in degrees. So I'm going to find the answer in degrees. And I end up with the tangent is equal to a negative 53.1 degrees. That is not in the interval. That is the negative rotation. Now remember, tangent inverse is only defined between negative 90 degrees, not inclusive, to 90 degrees. So the fact that I get a negative 53 just tells me that that is the negative rotation. If I add a full rotation, so plus 360 degrees, I will actually get this angle that I have right here, which is the 360 plus that 53.1. And the angle that I get is 306.9. Yep, 306.9. Okay. So to write it in the way that they wanted, so my vector is going to be my magnitude multiplied by, and I'm going to write the cosine of 306.9 degrees, comma, the sine of 306.9 degrees. Now, that's the answer. I'm done. As a check, if I put my calculator 306.9 degrees and multiply it by 5, I better end up with a positive 3. If I, in my calculator, do the sine of 306.9 degrees and multiply by that 5, I better end up with negative 4. But this is my answer. That is my answer. Okay? So, wrapping this all up, we have a magnitude and we have direction. The way in which we find our direction is by doing the tangent inverse of the b over a, or in other words, the y value over the x value. Now, you got to remember about where it's going to be defined and where you actually are standing. In this example up here, it's defined, the tangent inverse is only defined in negative 90 to 90, which means that when I got a negative 53.1 and I was required to be in the interval between 0 and 360, I had to find the coterminal angle to the negative 53.1. Similarly, if I end up in quadrant 1 based on my tangent inverse, make sure you're truly in quadrant 1 and you're not down in quadrant number 2 or quadrant number 3, because a tangent in quadrant number 3 is also a positive number, so you have to know where you're standing at all times. I would recommend you draw the vector that you start out with so you know where you are. The 0 vector is the vector that is 0. So in other words, it has no direction and it has no magnitude because you're really sitting at the origin. We have to talk about the 0 vector so that we can talk about having the additive inverse, because if you have one vector, say your vector v, is equal to 1, 2, the additive inverse would be negative 1, negative 2, and if I added these two together, you can see I'm going to get 0. So that would be the 0 vector. So we had to have the 0 vector. We can multiply the vector by the scalar. A scalar just means it's a number. It's a multiplier number that's going to multiply on both the x component and the y component. And the only time I get the 0 vector when I multiply my vector by a scalar multiplication is if either the vector I start out with 0 or the scalar is 0. When we're doing vector addition, it is we add the components, the like components, or we subtract the like components as needed. Note this triangle inequality. It will be important later. We'll use it a couple of times later. Actually, it's kind of important all the time, but we're really going to focus on it later. But what it is basically if you add the two vectors first and find its magnitude, it's going to be less than or equal to the vectors if you find their magnitude individually. So let's do some easy vectors. So let's do 1, 1. This is going to be my v. I'm going to do my w, which is going to be, I'm going to put a bar over them with the arrow. It's going to be 3, 3. So the magnitude of v is going to be the square root of 1 plus 1, which is the square root of 2. The magnitude of w is going to be the square root of 9 plus 9. So in other words, it's going to be 3 root 2. If I take and add these two vectors, so v plus w, this is going to give me 4, 4. Now when I do this magnitude, I'm going to have the square root of 16 plus 16, which is going to give me the 4 root 2. The magnitude, well, actually, that's just that. And then I should say, then the magnitude, because they're not equal, then the magnitude is equal to that. That is the magnitude of v plus w. Okay. So, its magnitude of v plus w is actually going to be the same as the magnitude of each one of them. This is one in which we have equality. Now what happens if I would have made that a negative, right? So I have my w now as a negative. What's going to happen here is it's going to change this number. So instead of being 4, it's going to be -2. So when I do this inequality, this isn't going to be 16. This is going to be 4. So for this magnitude, you can see is going to be 20, which is going to be 2 root 5. 2 root 5, so 2 root 5 is less than, put in your calculator, confirm, the square root of 2 plus 3 the root 2. So here's an example in which the individual components, the magnitude of each individual vector is larger than the addition first and then the magnitude. Whereas my previous one, they were equal. This is one in which the individuals' magnitudes are larger than when I sum them up. Okay, so scalar multiplication just means that we multiply each component by whatever that scalar is, and when we're doing addition, we add components, and when we're subtracting, we subtract components. So first, let's go ahead and do the addition and subtraction as it's shown, and then we're going to do the graphing. So they want me to do v plus w, adding each component. I'm going to add the 1 plus 1, so this 1 plus 1 is going to give me 2. And this -2 and the -3 is going to give me the -5. Now, I'm just going to rewrite these over here so I can see them and I don't have to keep scrolling back because I want to zoom in on my graph here. Okay, so let's zoom in on the graph. So we're going to start with we'll call this my v vector. I'm going to go over 1 and down 2. So here's over 1 and down 2. Starting at the origin and going over to the right 1 and then down 2 because it is 1 comma -2. From there, I'm going to go my w vector, which is over to the right 1 and down 3. So I'm going to go over 1 more and then down 3. 1, 2, 3. So here's my w vector. My resulting vector I'm going to call u, and it's going to be equal to my v vector plus my w vector. And you can see that I have a vector that starts in the standard position, goes right 2 and down 5, which is exactly what I got here. Now let's do the next one in which we're asked to find 2w. So we're asked in 2v minus w. So the scalar says I'm going to go ahead and multiply each one of my components here by that 2 first. And so I'm going to have 2 and -4. From that, I'm going to subtract off my w vector. So I take this 2 and subtract off 1, and I end up with 1. I take this -4 and subtract off a -3. So that ends up becoming -1. So let's go over here and do the same thing. Now again, I'm going to have my v vector and 2 times my v vector, which is going to be 2 comma -4. So I'm going to do that first. So I go +2 and down 4. 1, 2, 3, 4. Here we go. Here's my tip. Now, my w vector, because I am subtracting off the w, what that does is changes the direction. In other words, it multiplies by a -1, the additive inverse. So it's -1 and then it becomes a +3. So I go back 1, so it's a negative direction, so I go to the left 1, and I go up 3. 1, 2, 3. So this is where the -w is. My resulting vector is that, which is 1 comma -1, which is what I got here. Now, I'm going to go ahead and zoom out and let you try these. So go ahead and pause it right now. Try both of these. And what we're asked to do is find v plus w, and then 2v minus w. Same here, v plus w. And then 2v minus w. So go ahead and try these on your own. Put this on pause, and then come back and see whether or not you have the same answers that I've got. Welcome back. So here we go. When I'm adding these, I'm going to end up adding these two. So I have 2 plus 3, which is 5, and negative 2 plus 1, which is negative 1. When I do the 2 times v, this is going to give me 4, negative 4. And then I'm going to add to it 3, I'm going to subtract from it. What was I thinking? I'm going to subtract from it 3 and 1. So I have 4 minus 3, which is 1, and negative 4 minus 1 more gives me a negative 5. Let's go ahead and graph these. Again, I'm going to put these over here so I can get my vectors when I zoom in on my xy. Okay, so let me zoom in, zooming in, zoom in. Okay, my first vector, again, I'm going to do in red, so that is my v vector. I'm going to go positive 2 in the x direction and down 2 in the y direction. Excuse me. And then from there, tip to tail, I'm going to do my positive 3. So I'm going to go right 3. So 1, 2, 3, 3. And then I'm going to go up 1. So tip to tail, that's where that one is. My resulting vector, you can see there, just by my graph, my resulting vector, we're going to call it u. As you can see, it is 5, negative 1. Similarly, when I scale my u vector, it's going to go positive 4. So let me go back to my red. 1, 2, 3, 4, and it's going to go down 4. 1, 2, 3, 4. So here is 2 times b. From here, because I'm doing a subtraction now, I'm going to go left 3. So 1, 2, 3, and down 1. Actually, I should have done that in blue. My resulting vector is this. And my resulting vector for this one then is a positive 1 and a negative 5, which is what I got there. Okay, last one. Let's just do the graphing part of it. Negative 2, 1. So I have v, which is negative 2, 1, and my w, which is 1, negative 1. So 1, negative 1. Okay. That was my W. So once again, this time I'm going to go to the left 2 and up 1. So here is my V. My W from there is I'm going to go right 1 and down 1. So it's going to go right here. And my resulting vector is this little tiny piece. Doing the quick addition, negative 2 plus 1 gives me a negative 1, and negative 1 plus 1, negative 1 plus 1 is 0. So that is my resulting vector, which is what I found there. Let's do the next one with a multiplication. So I multiply the negative 2 times 2. So now I'm going to go negative 4 and up 2. So this is 2 times my v. And then my w, because it's going to go in the opposite direction, means I'm going to go 1 more to the left, and I'm going to go up 1. So 1 more to the left and up 1. My resulting vector, this u, is going to be, you can see, is going to be negative 5, 3. Now let's just do the math really fast. So 2 times v, which is going to give me negative 4 and 2, and then minus the w, which is going to give me negative 1, positive 1. And when I add those together, you can see I get the negative 5, 3. All right. Let's take a look at the vector operations. We have the commutative property. So u plus v is the same thing as v plus u. We have the associative property. We have the additive identity, which means I add the 0 vector, and I get the 0, or I add the 0 vector to any vector, I get whatever I started out with. The additive inverse, which means if I take my original vector and subtract off itself, I get the 0 vector. I have the associative of a scalar multiplication. That means it doesn't matter if I multiply the two scalars first and then multiply it by the vector, or if I do one individually. I can also distribute the scalar, so I can add those two scalars together and then multiply it by my vector. Or I can distribute that scalar on the vector and then the other scalar on the vector and then add those two answers. And the distributive property of the scalar over the vectors means that I can add the two vectors first and then multiply by the scalar, or I can distribute the scalar onto each one of those vectors and then add the two vectors. We also have 1 times the identity vector times itself gives me what I start out with, and 0 vector times itself gives me the 0 vector. Now, let's do some applications. Woo, woo. Okay. So what I'm going to do is, when you're doing air navigation, everything's off of the north. So everything is off of the north. They're telling me the first part of my flight is 400 miles. That is the magnitude, and we're going to call that the first one V, because we can. So that is my first one, and then the bearing is 34 degrees, and this is off of the north. So my first vector looks like this. It's 34 degrees off of this. That means this is the actual angle that I want. So I'm going to take 34 and I'm going to subtract it from 90 to get the true angle that I want. So 34 subtracted from 90 gives me 56 degrees. So the actual one I want is 56 degrees. Now, what this first vector, my vector V, is going to be equal to my magnitude, 400 miles, multiplied by the cosine of 56 degrees, the sine of 56 degrees. Okay. The next part tells me that on some distance, I have a bearing of 162. So I'm going to call this vector W. So here's a vector W. This is the angle of 162 degrees. That is not what I want to use. Now, I don't know what the magnitude is, so we're going to call this vector W, and so my vector W is going to be my magnitude of W, which I don't know what it is yet, and then it's going to be the cosine of 162. That is not what I want. What I want to know, because I just want to stay, actually it doesn't matter if you have negative and positive angles, really doesn't matter. Let's figure out what this is a negative rotation, just this part of it. So to figure out that part of it is I take off 162 minus 90. That gives me 72. So this is a negative 72 degrees. If I want the coterminal angle, I can do that, but I'm just going to use the negative 72 degrees. I'm going to have everything off of, even though the navigation is off the north, I'm going to do all of my rotations off of the x-axis. Actually, it doesn't really matter. So negative 72 degrees, the sine of negative 72 degrees. Now I have my last vector. I'll do that in red. I'm going to call that U. My U vector, and I want to erase this other part because I'm going to be using red. So I'm going to put that in blue. This was the 54 degrees. My U vector is, I have no idea, but I do know off of the north, I have rotated a total amount of 308 degrees. So this is 308 degrees. So it's going to have some magnitude, and I have no idea what it is. And I really don't care, not at this moment. And then I have to figure out what its angle is. And the way I'm going to do that is I need to figure out how far I've actually gone to the x-axis to that point. So if I take the 308 and I subtract off 180, that's going to give me 128. So that is 128 degrees. So I have the cosine of 128 degrees, comma, the sine of 128 degrees. Now, what I know is if I were to draw all of these vectors, their tip to tails has to close. So Here's my first vector. This is vector v. My vector w, and then my vector u. And in fact, what I know by looking at my picture, what I have is I have my u vector plus my w vector is going to give me my u vector. And I know all my components have to match up. So, looking at it component to component, the 400 cosine of 56 degrees plus the magnitude of w times the cosine of negative 72 degrees has to equal the magnitude of u times the cosine of 128 degrees. Similarly, 400 the sine of 56 degrees plus the magnitude of w times the sine of negative 72 degrees must equal the magnitude times the sine of 128 degrees. So what we really have is two equations and two unknowns. So let's go ahead and put in our calculators and just get some decimal equivalents. So 400 multiplied by, oh, let's make sure that we are in degrees. And I'm not, I'm in radians. Make sure you're in degrees. Because otherwise, that will totally mess you up. Okay, so 400 times the cosine of 56 degrees is, so looking at this first equation, actually I'm going to do it, bring it down here. My first equation is 223.67 plus the magnitude of my w, the cosine of negative 72 degrees, which is 0.3090, and this is going to be equal to the magnitude of u. I'm going to do the cosine of 128, which gives me a negative 0.6156. And then I have 400, I'm going to do the next one, 400 times the sine of 56 degrees, which is 331.62 plus the magnitude of w, the sine of negative 72 degrees is negative 0.9510. And it's going to be equal to the magnitude of u and then the sine of 128 degrees, which gives me 0.7880. I have two equations. I have two unknowns. However you want to solve for it is your choice. I'm going to throw this into a matrix, but be careful. When you throw it into the matrix, you're going to want to make it look like the XY shenanigans. So in other words, what I'm now going to do again is I'm just going to write it in our regular XY form. I have 223.67 equals. I'm going to call this X. I'm going to call this Y, just because it makes my life easy. So I have 0.3090x, and don't forget it's a negative because I moved it over to the other side, minus 0.6156y. 331.62 is equal to, bringing that negative 0.95 to the other side gives me a positive 0.9510x plus the 0.7880y. I just use x's and y's because it's easier, remembering, of course, that x is equal to the magnitude of w and y is equal to the magnitude of u. All right, so I threw this into a matrix in my calculator, And I have my magnitude of x, or magnitude, I have my x, which is the magnitude of w, is equal to 11, it's terrible, 11, 12.456, and the magnitude of y is equal to negative 9.921.73. And you're thinking, how can a magnitude be negative? Well, that's just directionality. Say what? Remember, the way I drew this up here, notice how I have my drawing. My drawing of u is going back toward the x-axis, but really when I'm doing addition, my addition should have been something more like that, if you remember my tip to tail stuff. But because of the fact the way that I drew it, going back and closing it, I ended up with a negative. So that just tells me my magnitude, it's not w, by the way. It should be u. So my answer, because it wanted to know u, it wanted to know the distance, or the velocity, or excuse me, the distance of the final leg. Huh. So my answer is 921.73 miles. All right, let's take a look at the next one with Romeo. Oh, Romeo, wherever out there, oh, Romeo. With this one, we assume that it's static, which means nothing's moving. At this moment, it's just a snapshot in time. There's no movement, so it's not a dynamic system. It's a static system. It is not moving. So let's talk about each component. So we first have this force in this direction. Its angle is 0, so 0 degrees. So when I do this one, I'm going to have some force, and then I'll call it force 1. And it's going to be a vector, and it's going to be the magnitude of force 1, the cosine of 0 degrees, the sine of 0 degrees. We're going to have this force. But since it's 60 degrees off of the horizon, that means what we have is 120 degrees. It will have some magnitude, so we'll call it force 2. It's going to be the magnitude of force 2, and it's going to be the cosine of 120 degrees and the sine of 120 degrees. We have this last one, which is straight down. I'm going to call that f sub 3. This is going to be equal to the magnitude of f sub 3. Just don't feel like putting the arrows over, I guess, the top. Times the, and I'm straight down, so it's 270. The cosine of 270 degrees. The sine of 270 degrees. Now, let's see if we've got any of this information. They tell us that Romeo has a mass of 68 kilograms. And Juliet has a mass of 60 kilograms. So we need to figure out what their weight is, because that'll be the force. So to find their weight, we take their mass, their combined mass, and we multiply by gravity and make sure that we are in the metric units. And I end up with 122.6 newtons. Now, I know that all of my components in the x direction and all my components in the y direction have to match. The only force that I have is this one. It is their combined force, which was 122.6 newtons. Okay, so F3 we have, I'm going to take 1,226 times the cosine of 270, which is 0. And then we have the sine of 270, which is -1. So this ends up becoming 0, -1, 1,226. Units are in newtons. My F2, or my F1, is going to be the, how do I want to write this? I'll write it, yeah. Indecision is a bitch. So it's going to be the F1 magnitude. Cosine of 0 is 1, so it's just going to be the F1 magnitude, and then that's going to be the 0. Now my F3, or my F2 is the only one that's really kind of interesting because it's not has a 0. So F2 is going to be the magnitude, which is F2. And we have the cosine of 120. Cosine of 120, that's negative 1/2. That's going to be multiplied by negative 1/2. And then we have the F2 multiplied by the sine of 120, which is the square root of 3 over 2. And I am getting that stuff off the unit circle. Now what I know is all of my directionalities in the x direction, because it's static, should not change. So in my x direction, I have 0 for my f sub 3. And for my f sub 2, I have plus. I'm going to call this x because I can. I'm going to call my f1 force x. I'm going to call my f2 force y just because I want to make my life easier. So then I have x, and then it's going to be minus 1/2 my y. Because we're not moving, this has to equal 0. The other one that I have is this is the summation of the forces in the x direction. And it has to equal 0. Now in the y direction, I have the negative 1,226 plus the 0, and then plus the square root of 3 over 2 times my y. And this also has to equal 0, summation of the forces in the y direction, which I now can tell you what y is. My magnitude in the tension of the rope that is 60 degrees off the horizon. That is my y. So what I'll have then is 1,226 is equal to the square root of 3 over 2 multiplied by y. So y is equal to, I'm going to take that 1,226, multiply by 2, divide by the square root of 3, and I end up with 1,415.66 newtons. So that is my magnitude of the rope, the tension in that direction, which was off of the 60. So we know that we found F2, which is 1,400. This number is 1,415.66 newtons. That tells me, since the rope can take that piece of the rope, all the ropes can take the 2 kilonewtons. But this one is less than 2 kilonewtons. So we know that this rope right here is okay. It's not going to break. We also know the downward tension, which was 1,226 newtons. That one's not going to break. Now all I have to do is see whether or not it's going to work out for my x direction. So I'm going to go back to this one. And I have x minus 1/2 multiplied by the 1,415.66, because that was my magnitude, or my y. And this has to equal 0. So my x will be equal to half of that, so we're cool. So we divide that by 2, and the magnitude in that direction is 707.83 newtons. So this is 707.83 newtons. So we know that each magnitude is less than the 2,000, which was required. It had to be less than 2,000 kilonewtons, or 2 kilonewtons, 2,000 newtons. So we know that these ropes are not going to break. And that's it.